Hi all. Let's go ahead and take a look at your first assignment on Achieve. So this is where you will show me that you know the material for our class. I'll go ahead and share my screen here with you. And let's see, there we go. So now within the Achieve, I'll go to my Google Chrome. And once you're registered for Achieve, you should see a screen similar to like the one I have right here. And of course, you'll sign in. You'll have your username and password registered with them. And then once you log in, your course should look very similar to mine. I'll go to our class. Now, this opening screen's kind of vague. You're just like, well, there's nothing due. Well, okay, that's just because there's nothing due within the next 7 days. What you'll always want to do is go over to where it says view all assignments. And of course, you can also go to the grade book and things like that on the left-hand side. Your ebook is also posted here. Remember, I've also posted the ebook inside of Brightspace. So you have two places to find that. But you can either go to the course plan, which that's always a good option too. Before you work the section 5 assignment, I would recommend, it's not required, but there is a training assignment that allows you to see how that Achieve is wanting you to input answers. It may save a lot of time and hassle if you go through that training assignment. It does not take long. I think it has 10 questions. Might take you a total of 15 to 20 minutes to go through it, but it will save you hassle later on if you haven't used Achieve before. The first 4 chapters is Calculus 1 content. Our class starts in Chapter 5. Notice you'll see chapters 1 through 4, nothing is assigned, for reference only. Chapter 5, do the assigned homework sections. Each problem has unlimited attempts. You could maximize chapter 5 since that's where we're starting. Now, what you see here is if you wanted to read through what the book, this is the same thing as the ebook, same thing as if you opened up the traditional textbook, the section 5.1 introductory information. They also have a summary information, which is usually pretty good. And then the homework begins. Of course, that's what I'm wanting you to do. Each homework assignment is going to be worth 100 points. You could just use the course plan, go through and work all of the homework assignments. You see that I have June 12th set as the deadline for all of the Chapter 5 homework assignments. So you should be through with the Chapter 5 content by that point. Now, if you go into the assignments tab rather than the course plan, like if you don't want to bother reading through the book, that's okay. On the assignments tab, please remember to go over here and hit the view all assignments, and then it automatically just pulls together everything I have assigned for you to work. So we're looking at this first section, 5.1. I'll go ahead and click on that. Now, as we're going into 5.1, the screen that I have will not be the screen that you have. This is an instructor only screen. It just shows me what problems out of the textbook that each of the assigned problems is similar to. Like you can see, there's a problem similar to number 2 out of the textbook, number 9 out of the textbook, number 13, number 14, number 19, and so on. So it just shows me what problem out of the book it's similar to. So there's no problem on Achieve that shouldn't have a corresponding problem out of the traditional textbook. But now I'll go ahead. This is what your page will look like whenever you go into it. This is the student page, if it will load. Sometimes it takes a while. Okay, so now let me go ahead and what I plan to do in these videos, to not make them too long, is I'm going to do blocks of 10 questions. So in this video, I'll go through questions 1 through 10 in 5.1. I'll have another video 11 through 20, and then another one 21 through 29 for this section. So this section will have 3 different videos. Going ahead and looking at the first problem here with you. It says an athlete runs with a velocity of 12 kilometers per hour for 5 minutes, then 16 kilometers per hour for the next 4 minutes, and then 18 kilometers per hour for another 5 minutes. Compute the total distance traveled. No problem. All we have to do for this one is I'll go ahead and pull up my document camera here to show you my work. For this one, we know that what was mentioned in the problem is we're looking for the total distance. We know distance is equal to rate times time. So we have a rate of 12 kilometers per hour times a time of 5 minutes. Well, that's 5 over 60 of an hour, plus a rate of 16 times a time of 4 minutes, 4 over 60, plus a rate of 18 kilometers per hour times the portion of an hour, again, 5 minutes, 5 over 60. You take each of these values times their corresponding portion of an hour, since we were given times in minutes, and they wanted us to round to 2 decimal places. I did that with my calculator and I got a 3.57. We don't need to show that one on the calculator, but I'll go ahead and get my calculator primed and ready for when we do need it here. Let's see, maybe this calculator will show up better. Yeah, that one will show better. Okay, so I'll go ahead and put this in the, it was 3.57. Let me go ahead and make sure this doesn't disappear again. I will pin it to where that should stay pinned now, to where it doesn't disappear. Now I'll go ahead and check my answer here. Check answer, and Achieve says you are correct. Once you're correct, you can choose to view the solution if you like, but since you've already got the problem right, you probably don't need to view the solution. So I'll just hit next question. Now, this next question, and actually I do want to make this disappear for this question. This next question is kind of cool here. This goes in and it's telling you about how we can approximate area with rectangles under a curve. So in this problem, it's having us look at f of x is equal to x squared, and it's wanting to know the area between 1 and 3 underneath that curve. So you see what it's done now, and you can, this is an interactive display from Desmos that you can find different things. If I wanted to do 6 midpoint rectangles, 6 left-hand rectangles, and I can see how it underestimates the curve for left-hand. I can see how I really can't tell whether it underestimates or overestimates with the midpoint. And for the right-hand endpoint, I can see it definitely does overestimate the area under the curve. Now, in addition to that, you can also change the number of rectangles as you like. You can go down just one large rectangle up to as many as 20 tiny rectangles in this region. And you can see how your area overall is affected. So I know that the area under the curve is probably close to 9.07, but I also know that it's less than 9.07. Probably the best approximation I could get to that is if I dragged this over to the midpoint with 20, 8.665. I bet you that's very, very, very close. Okay, now, number 2, the media question here. Let's see if there's anything for us to do. I think you get credit for it by just hitting the button here. Yep, you'll see credit received. So he's just saying to do the exact same thing as what I was doing above, where you scroll around. I won't take your time and make you watch that with me. So you're welcome to watch that in yours, but he's doing the same thing I was doing, is just scrolling it around, seeing the different size of rectangles in there. So all I had to do is hit play, and I got credit for number 2. Yay. Number 3. So it's having me use that dynamic figure now in a question. It says the dynamic figure shown at the right-hand endpoint, midpoint, left-hand endpoint approximations for the area under the curve y equals x squared on this interval 1 to 3. Use the slider to control the number of equally spaced subdivisions ranging between 1 and 20. Use the second slider to toggle between right, midpoint, and left endpoint approximations. All right, no problem. What is the true given that f is increasing? What is true given that f is increasing on the interval 1 to 3? Well, we have a function that is increasing between 1 and 3. And what is given is we know that the left-hand approximation is always going to be less than the midpoint approximation, which is always going to be less than the right-hand approximation. Let's see if that's what they talk about each down here. For each value of n, the nth right-hand endpoint approximation will be less. Heavens no, the right-hand will be more. So it's not the first one. For each n, the nth right-hand endpoint approximation will be equal to the left. Not true. For the next one, the relation between the nth right and left endpoint approximations will be different for each n. The relation, the proportion of it, that's not, I mean, could be true, but not necessarily. The fourth one, for each n, the nth right-hand approximation will be greater than the nth left endpoint approximation. Absolutely. So on one it could be. And in fact, we know that the right will be greater than the midpoint, which will be greater than the left. We go up to check answer, and it says correct. Move on. The fourth one here, again, it's referring to that dynamic figure. And the question here, this time it says, as n increases, the width of each rectangle gets infinitely small. Approaching but not equal to 0. What is true about the approximation for the area under the curve? Well, we talked about this in the notes. The more rectangles you have, the better your approximation is going to get. So it says the approximation approaches the precise area under the curve y equals x squared over the interval 1 to 3. Ding, 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 ding. Approximation approaches 0. No. It cannot be determined. Of course it can be determined. And the approximation approaches infinity. No, no, no. It has to be the first one. So as the number of rectangles approaches infinity, the approximation gets better and better and better to the actual evaluation of the area under the curve. Gorgeous. Correct. We move on. Now, number 5 is again one where I'll have to show my work, which I've already done for you, so wouldn't take too long in the video. So notice the function that they give us in this problem is f of x is equal to x squared minus 3x plus 6 over the interval 1 to 4. So in this interval, I know that my delta x is going to be b minus a. We're trying to find R3 and L3, so we have 3 subdivisions. So I said 4 minus 1 is 3, 3 over 3. Each of our delta x values is going to be 1. So the width of each of our rectangles is 1. Now, R3 is going to be the summation from I equals 1 to 3 of f of a plus I delta x, 1 plus I, in this case, since delta x is just 1, times your delta x is 1. So we're going to have 1. Now remember, that very first rectangle is going to go from 1 to 2. The second one would go from 2 to 3. The third one from 3 to 4. If you're using the right-hand endpoint, the heights of your rectangles are going to be at f of 2, f of 3, and f of 4. You can see that using your formula, or if you just drew it out, you could see it. But if your very first rectangle is I is 1, you're going to be looking for f of 2. When I is 2, you'll have f of 3. When I is 3, you'll have f of 4. So we have the common width times the summation of the heights. Now, each of these heights, what did I do to get to this? I plugged each value into my function here. So notice you could easily do that. And in fact, it's probably most easy just to type the function into your calculator's y equals screen. This was x to the second minus 3x plus 6. I'll just go zoom 6. We don't really care too much about what the function looks like. But now when I did that, all I would have to do is hit trace. I need to know what the y value is at 2. When I hit f of 2, I'm getting a 4. What about the y value at 3? Well, that's just 3 squared minus 3 times 3 plus 6 should be 6. And we see it is. And then when I plug in the 4, you get your value of 10 there. That's probably the quickest and easiest way to get those y values. Now we just say, well, then our area under the curve is going to be the common width times the summation of each rectangle's height. And we can see that's going to be 20 times 1 for an area of 20. Now, this curve is increasing from 1 to 4. So we know that that is an overestimate of the true area under the curve. The left hand should be an underestimate. And we can say, well, the left hand is just where I starts at 0. Why does I start at 0? Because we need our very first height to be f of 1. Or we need our second height to be f of 2 and our third height to be f of 3. So whether or not you do this part doesn't really matter. I like to see it, but you don't have to. We can say, well, this problem L of 3, it's going to be the common width 1 times the summation of our heights. The first rectangle's height is f of 1, second is f of 2, third is f of 3. We take those, plugging it into our function, you'll see I got 4, 4, and 6 for each respective height. Whenever I add those together, I get 14 times the common width of 1 for 14. So now when I go back up to my problem, I'll say, well, I know that my right-hand endpoint estimate here was 20. My left hand was 14. We go to check answer. And of course, it's going to say correct. We go on to the next question. Next question's again, one that's involving media. So we'll use this to help us out. And this is another one that's going to give us participation credit by just watching a video. So again, they're going to be talking about how the number of, as the number of rectangles increases, your approximations is going to improve.
As the number of rectangles increases, the sum of the areas of the rectangles gives a better and better approximation of the exact area.
Gorgeous stuff. And you can see as the number approached infinity, it just fit a nice solid triangle for the area under the curve there. Now, for all of these videos like that, there's nothing to work, so don't get confused. As soon as you hit the play button, you've got credit. I'll go to 7. Now, 7 is going to base a problem off of that, and it's asking us to find the value of r of 2. Well, all I have to do is go up here and say, well, that's the right-hand rectangle rule with 2 rectangles in there. Yeah, there we go. There's when 2 rectangles and it says r of 2 is 12. Boom, done. I know you're thinking, that's too easy. Yeah. Next question. Now, this one, it's trying to get you to see what happens as the number of rectangles approaches infinity. Now, this is f of x is equal to x, and we know we're trying to find from 0 to 4. We know the height here is 4, the base is 4. You really could just say, hey, area is a triangle, 1/2 base times height. 1/2 4 times 4 should be 8. 1/2 16 is 8. But to see this with the rectangles, you're just scrolling those rectangles over. And please notice, as those number of rectangles increase, that area r sub n is approaching a value of 8. And that's what they're trying to get you to see. As the number of rectangles increases, and notice, eventually it's going to, now it just stops at r of 50, and then if you scroll over one more, it's just saying, hey, as you put more and more and more, the area is going to go to 8. And so as n increases, what value does r sub n approach? And our answer is 8. Check that, correct. Number 9. Number 9 is another one that we'll have to show some work on. So it's asking for L sub 4 and R sub 4 of 2x squared. And this is from 0 to 3. So if I need L4 and R4, then delta x is just going to be the change in your x values, 3 minus 0 divided by the number of rectangles you want, which is 4. So we know the width of each rectangle is going to be 3/4 of a unit. Now, L sub 4. My formula for that, f of a plus I delta x, would be f of 0 plus 3/4 I in there, times our common width of 3/4. And we're going with 4 rectangles that go from I equals 0 to 3. The same thing for R4, except your I value starts at 1 and goes to 4, since you need the height of your first rectangle to be determined at 3/4 instead of at 0. Now, either way you do it, whether you do this or just do it this way, you say, well, the common width is 3/4 times the summation of your heights. Your first rectangle is going to have a height determined at f of 0, then f of 3/4, f of 6/4, f of 9/4. What do we do with all these functional values? You simply plug them into your function here. F of 0 is 0. 3/4, you'd have 2 times 3/4 squared. It's going to give you 9 over 16 times 2. That's where the 9 over 8 came from. 6 over 4 squared would be 36 over 16 times 2. 36 over 16 times 2 would be 36 over 8, and then that reduces down to 9 over 2. And then the last one, 9 over 4 squared would be 81 over 16 times 2 gives you 81 over 8. You take 3/4 times the sum of those heights, you get 11.813. Similarly with the R sub 4, you'll say, well, the L sub 4 and R sub 4 are going to share 3 of the same heights. It's going to have all 3 of those values. It just doesn't have the very first one. Instead of F of 0, it's going to have F of 3. The other 3 heights are always in common. So it starts at the second one because the second height in L4 is the first height in R4. So we have F of 3/4, F of 6/4, F of 9/4, and then F of 12/4, or F of 3. Whenever you plug those into the equation, the only thing we haven't done is the F of 3. That would be 3 squared is 9 times 2 is 18. That's where that height came from. You multiply 3/4 by the sum of those heights, I got 25.313. Let's check those values. So I have 11.813 for the first one, and then the R4, which we know is an overestimate, 25.313. And it said to 3 decimal places, so this should satisfy it. We'll check that answer, and it's saying correct. We move on. Number 10 here. So it's wanting the M6 approximation. 6 is about as many as I would ask you to find by hand. That's getting a bit by the time you have to find 6 different rectangles in there. So I found the M6 approximation for f of x is equal to the square root of 5x between 2 and 5. If you need 6 rectangles in there, you know that the width of each rectangle is going to be the ending point minus the beginning point. 5 minus 2 divided by 6. So we get 3/6. The width of each rectangle is 1/2. Now, the way I would need to think about this is that means that your very first rectangle would start at 2 and end at 2.5. But remember, its height is not going to be determined at 2 or 2.5. It's at the midpoint. That's why I have f of 2.25. That's the midpoint of my first rectangle. And then every one after that, it's easy because you say, well, you're going in increments of 1/2. So then the next height is going to be the midpoint between 2.5 and 3, f of 2.75. The next one's another half of a unit down, f of 3.25, another half of a unit down, the height at 3.75, the height at 4.25, and your very last rectangle's height, that's going to be the rectangle between 4.5 and 6. Its height at the midpoint is going to be f of 4.75. So once again, in a problem like this, it's so much quicker and easier if you'll go ahead and just let your calculator make the problem simple. I'll just graph out the square root of 5x on it. And then we can say, well, we're looking for this at these values here. So I'll just say my x values between 2 and 5, and zoom 6 should be fine. Here's my square root function coming in there. And then I can say, well, my first one, I hit trace, f of 2.25. I get the 3.354. Now, on Achieve, it asked me to give my answer correct to 2 decimal places. To ensure that my answer was correct to 2 decimal places, I maintained 3 throughout the problem. So I put 3.354 for the first one. And again, remember where that 1/2 came from. That's my common width times the summation of the heights. My second height, 2.75, that's where the 3.708 came from. 3.25 gives me a height of 4.031. The 3.75 gives me a height of 4.330. And then 4.25 gives me a height of 4. Now notice that 6097, that's going to round up to 4.61. And then my last one at 4.75, I got the 4.873 for that one. So then I took 1/2 times the summation of my heights, and I got the 12.45 rounded to 2 decimal places. We'll check and see if this matches with what Achieve wanted. It should. And it does. Okay, guys, so this will be the end of my first video I do with you here on Achieve. I'll have 2 more for this section to help you out if you have any other questions. And even if you had questions in any of these first 10, let me know. They should be very, very similar to what we've just done together. This is going to be some fun stuff.